Okay, now we look at the 1900s and the atomic development. The question I pose is, what is the driving force for the discovery of the atom? As much as we would like to think that it's purely human curiosity that drives us to know the unknown, it was truly about war and control. And that's what the obelisk here is. It symbolizes our very first nuclear detonation here on American soil. It's called the Trinity Site. And it's in New Mexico, White Sands Missile Range. Our first player is Ernest Rutherford. Three things that you should know about him is the proton, gold foil experiment, and Rutherford's model. Bohr and Geiger both work with him. In the bottom right corner, you will see his experiment. He takes alpha particles and emits them through a colorimeter. The colorimeter gathers a very thin beam of the alpha particles. Those particles hit a piece of gold foil. Now, whether or not this gold foil was very thin, thick, we're not real sure. But we consider it to be fairly thin. If the only particle that was there was an electron, then the theory was as the beam went through, it would be attracted to the negative and nothing would come out. But that's not what we saw. And if it was just empty space between the two and there was nothing that was like the alpha particle going through, it'd go straight through, no diffractions. But it didn't. It deflected from its normal path and hit some detectors. And because of deflection, he used his concept of physics and figured out that there must be something positive on the inside of the nucleus, which he deemed the proton. And there would be these electrons on the outside. So on the left side is the starting model, which he took J.J. Thomson's idea and modified it, and then modified it further with this planetary model. He related it back to the solar system because we understand our solar system. And so that was his model. And here comes Niels Bohr. Niels Bohr worked with Ernest Rutherford, but he disagreed with his model. He felt that it did not explain the atomic structure. And the reason is if you have something that's positive and something that's negative, under our natural laws, they're supposed to be attracted to one another. And this is not what we're seeing because we're alive because the nucleus and the electron stay separated. Okay? So he deduced that there must be some kind of strong force that keeps the protons and electrons separated. He used hydrogen as model, but it didn't work with all levels, but he did give us a starting point for the model. We do give him credit with also helping Meitner and Friis come up with the idea of fission. He did join the British Alloys delegation following his escape from Nazi-occupied Copenhagen. He did send coded messages to let people know what was going on before he had fully escaped, and the secret committee, MAUD, was named from one of his secret coded messages. And he did work on the very first British cyclotron, which is basically a particle accelerator, which was designed originally by Ernest Lawrence, which was an American. Here is this model. It looks very similar to Rutherford's, but he does talk about a force that keeps them separated, and he also talked about energy levels. And energy levels we'll get to when we talk about quantum model. Here's Hans Geiger. Hans Geiger developed the very first Geiger counter. He did work with Rutherford. The significant thing about the Geiger counter is it enables you to detect radiation, which is always important. Anton Henry Becquerel, we say that he is our father of finding nuclear radiation. He did earn a Nobel Prize. He did work with the Curies. In the bottom left, you'll see an image, and they will say this is a clear image of the salt. His basic experiment was that he took a uranium salt and he placed it in a dark room and placed a photographic plate next to it. And he got an image. The question that he was trying to answer was, does uranium emit its own light, or does uranium use the light from the sun? Which is why he closed it off and put it in a dark room to see if it was the sun or if it was, its own radiation. And since he figured out that it was emitting its own light, it was therefore radiating, and so therefore he starts working on the idea of nuclear radiation. Pierre and Marie Curie, they did work with Henry Becquerel. We give them also credit with finding nuclear radiation. Because of their work, it will lead to the development of the quantum model. Marie does die of radiation poisoning. Her daughter also continues her work in radiation work, and will actually be significant during World War II in preventing the Nazis from getting heavy water and thus preventing them from developing the very first atomic bomb. Henry Moseley. Henry Moseley died in 1917, which is during World War One. But before that, he organized the atomic number based on X-ray crystallography, and as we saw earlier, we talked about slicing a crystal and looking at the pattern and deducing what the relationship is, and therefore figuring out about the atomic structure. And that's really what he's known for. And so his work enabled us to rearrange the periodic table. He noticed that there was a pattern with the protons, and this has to come after Rutherford's experiment. He subjected the elements to X-rays. He knew their X-ray frequency. He knew their protons and developed and noticed a relationship. This relationship is called periodic law, and periodic law means that we have a reputation of characteristics along with the repetitive properties that can be distinguished with a mathematical relationship. The part about the mathematical relationship is the most important part here because it basically gives this standing. If it was just a pattern and characteristics and you couldn't back it up with math, it doesn't give us as much a foot to stand on as if you can say, I have the math to back this up. So the math was very important for proving his point.